All right, what's going on, everyone, and welcome back to our mechanics and materials sequence. And this video is an example problem that shows you how to apply the torsion formula, and probably an introductory example problem. So, if you've never done an example problem calculating the shear stress due to internal torque or torsion, then this is the video for you. All right, so what we're going to do is what we're given here is this uh, solid circular shaft with some length that really we don't need for the shear stress calculation, and with a bunch of concentrated torques applied at points A, B, C, D, and E. And the diameter of this is 50 millimeters, so the shaft, and it's constant. It's a uniform cross section all the way through. There's no changing of area. And what we want to find is the maximum shear stress along the path. Okay, or I'm not sorry, along the x-axis. Okay, so where is the maximum shear stress occurring? And the way we're going to go about this is we're going to divide this thing up into segments, calculate internal torques, then draw the internal torque diagram. So if you've drawn an internal shear and moment diagram before, then this is going to be relatively straightforward. And then we're going to apply the torsion formula and calculate that shear stress that's induced by torsion. So let's get to it. The first thing is to calculate internal torques. And really, what's important is that you have to know what segments that you need to cut at here. And really, the rule for cutting segments, this is kind of my rule of thumb, okay? And in fact, it usually works. Cutting segments, uh, the boundaries of the segments, or cut segments, or boundaries of segments, segment boundaries. Let's call it segment boundaries, okay? Segment boundaries, or places where you need to cut in between, are at the boundaries are concentrated loads to the beginning or ends of distributed loads. 3, let's see, supports or reactions due to supports, where support reactions are, and any sort of geometric discontinuity. So a sudden change in area. So if you attach on something with a different diameter at just this other place, you join two pipes together, and all of a sudden one pipe has a different diameter than the other, that would be a geometric discontinuity. Okay, and usually that will do it, and those are the identifiable segments. Okay, so let's look at this right here. We have a concentrated torque at A, B, C, and D, and then we have a reaction or a support at E. So we want to make sure that when we cut in between each of those. So here A, B, B, C, C, D, D, E. All right. Now, so we're gonna cut in between each of those. I prefer to draw this thing in 2D. This thing is hard for me to tell in 3D a lot. So here, just in 2D, I would have here is my fixed end. I have here at point A, I have a torque. And if I use a right-hand rule, thumb pointing in the double arrow, here is my 68 Newton meters at A. Call that point A. At B, I've got going the other way, 20 Newton meters. And then at D, I've got here 49 Newton meters. And then here at D, I've got, so B, C, D, I got this 35 Newton meters. There we go. And then this is my reaction at E. Okay. And so now I know that I want to cut here, 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 and here, one at a time. So I'm going to cut, let's look at segment AB. Segment AB. And here, with segment AB, I have here, bam, bam. And you might want to fast forward through all this if you have a feel for it already. But here, 68 Newton meters. I draw my internal torque as positive here. And positive internal torque, initially I draw it positive. The positive internal torque is away from the surface of the cut. Kind of like the direction of a normal force, but with the twisting going on. Okay, so here, this would be the way I've drawn this with respect to this cut right here, is that this is a positive internal torque. So I'll call that torque at AB. I sum the torques. The torques, let's say any torque double arrow going to the right is considered positive. equal to 0, and I would have TAB minus 68 Newton meters equals 0, and that tells me that the TAB, the internal torque of AB, is 68 Newton meters. Good, right? Then I look at segment BC. So here I'm just going to go one at a time, segment BC, and here again you may want to fast forward this if you are feeling good. Okay, so here segment BC, so I want to make sure I include all the external forces. 68 Newton meters. I looked at the cut through segment BC here, and here this one is 20 Newton meters, and then here again this would be internal TBC right here, and I sum the torques equal to 0, positive to the right, or globally positive, then this TBC plus 20 Newton meters minus 68 Newton meters equals 0, and that tells me TBC is equal to 48 Newton meters. And just to know, the reason I make the cut and I look at the left side is because I never found the reaction at E. Okay, so if you wanted to look at once you make a cut, you can look at the left or the right side. But if you want to look at the right side of the cut, you have to make sure you find the reaction at E. Okay, it's as simple as that. Otherwise, you won't be able to solve it all out, or you'll get a bunch of inaccurate numbers. Okay, and then the same thing, we keep repeating it. Segment CD. So I'm going to pause here, give you the kind of the equations for segment CD and DE, and then we'll continue. All right, so here are my internal torques. I have my AB, 68 Newton meters, segment AB. Segment BC has 48 Newton meters. Segment CD, using my equilibrium equations for this free body diagrams here, I got 97 Newton meters for CD and 132 Newton meters for DE. Okay, so now I want to draw my internal torque diagram, and I have all the internal torques that I need. Just like, when we draw shear diagrams, because I don't have any distributed loading here or anything going on in between these concentrated torques, I expect this to be kind of just a stepwise diagram of sorts, where there's just, so here, if I set this up, I'm going to draw this thing in 2D again. So down here, I kind of went ahead here. I have this internal torque diagram. I've got my external loads. I already made cuts through each of these. I know what the internal torque values are. So here, I know that going, if I just, right here, wherever I have quote-unquote discontinuities, okay, or concentrated torques, I'm going to draw this vertical line, just like I would in a shear diagram for a beam, where I have point loads or concentrated moments. I know that these are going to be segments where I'm interested at these points. This was A, B, C, these points here, and this was D, and this was E right here. And I have, let's see, I'm just kind of setting up my graph here, and bam, like this right here. I have this right here, and I will say that this is my, it doesn't really matter, but this is my plus X direction. It's kind of backwards, if you will, but it's okay. And then vertical upwards, this is torque, internal torque that I would experience. And I know initially here that I calculated here, I had initially 68 Newton meters here in segment AB, and it's going to be constant. Wherever I cut between segment AB, I know that I have a 68 Newton meters inside. Then in segment BC, I had an internal torque of 48 Newton meters, so it drops down a little bit, or drops down, and to be precise, here we'll call this 48, 48 Newton meters. And you'll notice that here, just like with concentrated forces on a beam, this displacement, or this drop that occurred, was the same as the magnitude of the concentrated torque at B of 20 Newton meters. And then in segment CD, I have I've got, let's see, 97 kilonewton meters, and I jump up to 97, which we'll be able to say it's about right here. 97 Newton meters, sorry, not kilonewtons, Newton meters. And then here I jump up another 35 Newton meters to this 132 Newton meters. So I'll put that right here, and this would be 132 Newton meters. And again, notice that these differences are the same as the concentrated torques that are applied at those points here. And this would be my internal torque diagram here. Bam, just shade it in for effect. And I also know that my reaction here, if you will, on this side right here, is also going to be a torque this way of 132 Newton meters in order for me to be in equilibrium. Okay, so that's something that we found out just from looking at this diagram and doing our equations. All right, now, oh, it's all good, but that looks good too. Hey, all right, now we want to calculate the stress, the shear stress and the maximum shear stress along the length, so that, you know, eventually we might want to do some shaft design or something that's associated with all these torques that are being applied. So we want to calculate shear stress or maximum shear stress. And the maximum shear stress, because this is constant diameter, right? Our shear stress formula, tau, is equal to the internal torque times rho divided by J. And if we want the maximum shear stress, which will occur on the outer edge here, then sometimes you might have used some formula, tau max equals T times C over J. It doesn't matter, as long as the radius is the outer radius. That's where your maximum shear stress is going to occur, at a point along your shaft. The other thing you need to find is the geometric properties. So here, J, the polar moment of inertia, or the resistance to twist, is pi over 2 times the radius of the shaft, I'll call that C, to the 4th. And since my diameter was 50 millimeters, diameter is 50 millimeters, my radius of the shaft, this circular cross section, is 25 millimeters, and I just have to substitute real fast. Pi over 2 times 25 millimeters to the 4th, and that is just, let's see here, 613,592.3 millimeters to the 4th. And just like moments of inertia, or area moments of inertia, you know, the units are length to the 4th, and this is millimeters to the 4th. This is polar moment of inertia. And so our maximum shear stress is also going to occur in terms of along the length at the location of the highest internal torque, which is segment DE. So max shear stress in segment DE, and this case right here, tau max, is equal to the torque, 132 Newton meters, times the radius, which is 25 millimeters, divided by 613,592.3 millimeters to the 4th. So all I did was plug and chug, and I want to make sure I convert the meters into millimeters. So 1,000 millimeters per meter, bam, and that lets me, you know, kind of cross those out, keeps everything in millimeters, and that gives me, when I go through and I plug and chug into my calculator, hopefully this is correct, I get 5,370. Oh, whoa, not 5,000. Oh, I can't even read my own writing. 5.378 newtons per millimeter squared. And a newton per millimeter squared just so happens to be a megapascal. Okay, so 1 newton per millimeter squared equals 1 megapascal. That's always convenient. And another problem, sometimes you'll see a kilonewton per millimeter squared, which is equal to 1 gigapascal. All right, so not only did we calculate shear stress and go over internal torque diagram, I also gave you a little tidbits on units. Okay, so that way, you know, it makes life a little bit easier. All right, hopefully you enjoyed. Let me know if you have any questions, and don't forget to box your answers. And in another word, done.